In this video, I'll show you how to make a unipolar PWM in Simulink for a full-bridge inverter. So if you're not familiar with a full-bridge inverter or a unipolar PWM, I have other videos on that. And I also have a mini course on that. You can see the link in the description. So let's get started. We will do it from scratch. So first we want to make the full-bridge inverter. So we need some switches. I'll just use IGBTs with diodes. And then we just connect them. And then we need an input voltage, which is a DC link voltage. And I have predefined a voltage, which is called V in. Now, if you're interested in this simulation model, you can go to the link in the description to get it for free. So now we have a full-bridge inverter. Now we need to make the gate signals. So I'll just define the ports first. So here we have S1. And this will also have S1, but we need to invert the signal. So I'll just add a NOT. And then we can do the same for the other leg. That was a bit too much. We can just move this a bit to the side to get some space. So this is called S1, S2. And then we want to measure the output voltage. So we add a voltage measurement. We can make this just a bit higher up. So here we have the voltage of one leg and then the other leg. Oh. And then we need a scope to see the measurements. So now this is the full-bridge inverter. Now we want to make the unipolar PWM signal. So in this document, I have a block diagram, which I will follow. So this is explained in the document. And I also have a video, which explains that. So we will follow with this one. So basically how it works, we first generate the duty cycle. So we take the desired output voltage that we want, and then divide it by 2 times the input voltage, and then we add 0.5 to create an offset. And then when we have the duty cycle, we take 1 minus the duty cycle to get the other duty cycle of the other leg. And then we use PWMs to get the gate signals that we want. So we will just start with, let's say we start with D1, the calculation of D1. So then we first need a reference voltage that we want. So this is the reference voltage that we want the output voltage to become equal to. So that would be a sinusoidal voltage with an amplitude of the square root of 2 times, I think I predefined a variable here. And then we want a frequency of 50 hertz. I've also predefined that. And then we need to multiply with 2 pi because this is in radians, not hertz. So this is the reference voltage that we want. And now we need to divide by the input voltage. So the input voltage here is just constant. So I will just add a constant. But you should ideally measure the voltage. So we have, V in is the voltage. It's 400 volts. And then we need a gain because we need to multiply it with 2. And then we may have to add a divider. So then we have the duty cycle, but we need to add an offset. So it becomes between 0 and 1. So we need to add a constant first, which is 0.5. And then a sum to add those together. So now we have the duty cycle. Now we can make a PWM to get S1. So we first need a carrier. No, we need a repeating sequence to make the carrier. So I will just make a triangular waveform. So I need to add some time points here. So after half a switching period. So FSW is the switching frequency that I've also predefined. Then we need to add another point after one switching period. So at time 0, we want 0. After half a switching period, we want to have 1. And after one switching period, it should return back to 0. So then we get a triangle waveform. And then we need to compare this with the duty cycle. So we need to add a relational operator. Like this. So now, when the duty cycle is larger than the carrier, we get 1, which is what we want. So this is the gate signal 1. Now we need to first find the gate signal 2, the duty cycle 2. I can just call this D1. Now we need to find D2. So we can add, if we just look at it first, we have 1 and then minus D1. So here we have the 1. And then I just copied the sum there. So this should be the other gate signal, the other duty cycle. And then we can actually use the same carrier. So this would be S2. And then this is not at D1, it's D2. Just move. Oh, it doesn't work to move it. Yeah. So this is basically the PWM. So let's try to see if it works. So I will just plot for one period of the reference voltage because we have 50 Hertz. So, and we also need a power GUI. And 1 microsecond is okay. So we don't want continuous because the PWM doesn't work with continuous time step. You could actually just change the sampling time in Simulink itself, but yeah. So we have done something wrong here. You can see that we have overmodulation. So let's have a look at the duty cycles. So if you add a scope, just to see how it works, you can actually also add the gate signal here. You can see what it says. Yeah, so we have overmodulation, which means that the duty cycle is larger than 1. So this would obviously not work. We need to find the error in how we calculate the duty cycle. So I see it here. It's because we didn't multiply with 2. We only multiplied with 1. So let's try it again. So now we get a duty cycle between 0 and 1, which is what we want. So then we can look at the output voltage. Now you can see that it looks sinusoidal, right? Because here it's on average 0, and then here it's on average maybe above 300, and then 0, and then minus 300, and then 0. So this looks sinusoidal. So if we just add a simple filter, we can filter out the sinusoidal signal. So first we can add an inductor. Yeah, 1 milli is okay. And then we can add a capacitor because we want to add a LC filter, which is quite common for these applications here. This should be a bit larger. Now this is not a well-designed filter, it's just something that I've quickly made. And then we need a resistor to add a load. because this will not work without a load. So 10 ohms is nice. And then we can try it again. I forgot to measure it, so we need to add a measurement on the output voltage. So here you can see that we get a sinusoidal signal. So this filter is not perfect, obviously. You can see that we have some ripples, and it will also give an offset or a phase shift of the voltage, and maybe also an amplitude offset as well. But you can see that this PWM works. So again, if you want this simulation model, you can go into the link in the description. And if you want this course here, where I explain now bipolar PWM, and then this standard unipolar PWM, and a variant of a unipolar PWM. So this was the standard unipolar PWM. And then I also explain how a full-bridge inverter works and how a PWM works. And I also compare each of these methods here. So if you're interested, you can go to the link in the description for that.